Okay, we're gonna start every class, review this, make it an essential part of what we do here. What's our one goal? Do you guys remember that? And what's our one and what's the mission? How's the method that we're gonna do that? Excellent obedience, excellent. Okay. So I have who has the Bible with him? Oh, fantastic.
Yes.
Can you find it's in First Samuel? And I got highlighted in here. So I have a little plan. You know, I learned something. That regardless of where you're at, God still kind of is the most important part of what we do here. So 1 Samuel 15, and then go ahead and go down to verse 22. And while you find that, I'll give you the quick context here. I'm a Bib Lit major, so I think it's funny that I'm even teaching this class. What's happening is we got a king named Saul. He's kind of a bigwig guy. He gets appointed to be king after the period of the judges. What happens is he's commanded to go fight a battle to conquer the Amalekites and to destroy everything. Okay, pretty simple instructions. So what he does is he goes, beats up the Amalekites, but instead of destroying everything, he saves some of the riches, the cattle, some of the wealth, and he saves it with the intention of keeping it for himself. So is he obeying God? Well, he defeated the Amalekites, but did he obey God through the way that he defeated the Amalekites? And so his point here is going to be, and Samuel's going to confront him. So would you go ahead and read from verse 22 down to that quotation?
And Samuel said, "Has the Lord as great delight in burnt offerings and sacrifices, as in obeying the voice of the Lord? Behold, to obey is better than sacrifice, and to listen than the fat of rams. For rebellion is the sin of divination, and presumption is the iniquity and idolatry. Because you have rejected the word of the Lord, he has also rejected you from being king."
So the key is obedience is worship. It wasn't the sacrifice that was counted as worship. It wasn't the action that was counted as worship. But God was looking for Saul to obey. And when he didn't obey, then that was no longer worship, even though what it looked like is going to be worship. So this is definitely not chapel. We're in GC 411 something, okay? But this should still be worship, right? So when you leave chapel doors, you're in the air conditioning, so they try to like, oh, the Holy Spirit's here, you know, and all this stuff, and then you leave. And so then every Monday, Tuesday, and Thursday, then you live for yourself. And then you kind of forget that those little hours that you spend on Wednesday and Friday are not supposed to be isolated periods where you're in communion with God, but that communion with God should be something you carry with you throughout everything you're doing. Does that make sense?
Yeah.
So the Lord just wanted me to share this with you. So maybe we're solving math problems instead of singing worship songs, but when you understand that worship is obedience, then your attitude towards the mundane will be forced to change. So if you understand that you are carrying worship with you in your classrooms, you're carrying worship with you when you go to sit down and do your homework at night after when you want to be doing other things, when you realize that all of those mundane actions, if lived out in obedience, is the same thing as if you're standing in chapel and everyone's closed their eyes and raise their hands and singing, right? So we need to dispel this idea that worship is that restricted activity that you're going to do in corporate, you know, at church on Sunday or in chapel. And it'll change your mind about the way that you prioritize your life. Then it'll change your mind about the kinds of tasks that you have to do and potentially why you're being asked to do them, okay? So, as of one more thing, how many of you can say that I've accepted Jesus Christ as my savior, right? That's pretty straightforward. Now, how many of you have accepted Jesus Christ as your personal Lord? Okay. Do you know what the difference between Savior and Lord is? Yeah. So this isn't necessarily salvific. You're not going to get to heaven because you can differentiate, okay? But you are going to need to obey his commands. He's sending you into places as your Lord, and he's going to lead you. He's going to be your king. And you're going to obey your king, and you're going to go into these places to reach people who really don't know God. Okay? Cool. So office hours. The math department was kind enough to give me a little, there's a very cute little office down there. So how many of you know how to get to the I4 lab? Awesome. So when you go, as you're headed down to the I4 lab, there's that massive fancy glass wall door thing with the fancy lights and everything. So the very first right after that, there's a hallway that kind of splits. So I'm down that hallway, it's 1D30. So I'm going to go to the D2L shell and I'm gonna add the hours that I'm just gonna be in there doing work. So you can always come in anytime. You don't need to schedule an appointment because by definition, you're in this class, which means that you already have an appointment, which is when you walk into that office and I will give you my attention. Make sense? Okay,
And I have office hours too,
yes,
so feel free to come see me anytime.
yes, you have an actual like organized thing for that, for the cat. So on academia, you can reserve time slots with Dr. Harder and you do that up in 404 or the fifth floor. Okay.
Yes, we're in the old library, fifth floor area.
Does everybody know where to find Dr. Harder up there? Because I know they've changed everything in the library. Okay. So lab Fridays, there was a good question about what we're doing on Friday. No, this is not a lecture. And so the only times that we might use Friday for like lecture content is if it's a super dense week. So if we're trying to cover like a bunch of, later on in chapter 16, we cover, I think, 3 different coordinate systems and integration methods for those coordinate systems. That's just a high volume. So we might bleed over and use some of Friday to cover that. But for the most part, we're going to solve problems. That's what a lab is in a math class. So I'm not going to bother you with, computer stuff and all that disgusting technology. It's just going to be some pen, some paper, some problems, your brains, okay? The way I'm grading this is completion. Because if I graded it on accuracy, then there'd be a very high fail rate. These are designed to be tough questions. And the reason why they're supposed to be tough questions is because if you're never challenged before an exam, you're going to flake out at the actual thing. So these are harder than the actual exam questions. And that's the reason for that. Because when you get used to struggling with something and used to putting down effort and trying to solve something you haven't seen before, that's really all we care about in a math class. So do I care if they're accurate? No, not really. I care though if it's obvious that you're trying to solve the problem using your God-given brain with the definitions and the practice that you have done throughout the week. Okay. So the way it's graded is for every single question is worth 1 point exactly. And that point is being given for a solution or an attempt at a solution or evidence that you have thought about the problem and that you have an idea of how you're going to tackle that problem. Make sense? Those are going to be PDFs. I will be strict about that one thing because my computer is a potato. So I don't think I changed the D2L settings so that you can't even upload other files except for PDFs. So all it is I have, there's phone apps, there's everything. You can take a picture of it, it'll convert it to a PDF, throw that into the Dropbox. Okay. So the due date is always going to be 1 week after the lab is assigned. So this upcoming lab starts on Friday, which means that it's due
next Friday.
the next Friday. Sometimes the lab calendar, and I'll communicate when it's slightly different, but sometimes I'll give you extra weeks, just because to me, it doesn't make any difference whether or not you do it the previous or whatever. And sometimes I'll make the due date in a way that facilitates your exam review. So then you're doing the lab as part of your exam review so that you're not wasting time doing the exam and then having to do a random assignment afterwards. Make sense?
Yeah.
So is that fair? Okay.
Are the labs are we just gonna be in here?
Yes, so it'll be in this classroom on Friday.
Got it.
And then on D2L, it's just a PDF of problems. Okay. Let's get into, we're gonna do 13.4 and 13.5. Raise your hand if you did the readings before coming to class. Hi. Rebecca, what were the readings for today?
According to the course calendar, 13.5.
Excellent. Okay. So that makes you actually a little bit ahead. The readings were just through 13.4 for the cross products, but if you've done 13.5, you're on top of it. So we're going to quickly review some of the stuff that you already have seen before. Right hand rule. Why do we have the right hand rule with cross products?
Because their resultant vectors.
What specific piece of information is this giving us about a cross product?
The direction of the vector.
Exactly, direction. Okay, so recall, so since U cross V, so this is not a dot product, this is a cross product. U cross V, is this a scalar or a vector?
Vector.
Right, U cross V is a vector. That's a very important math word. So it's going to have what? Direction, direction, and magnitude. So again, what is the right hand rule giving us?
Direction.
Direction. So the right hand rule is providing us with this information right here. And then we get the magnitude from this formula that we covered on, I believe, Monday. Where it's the UV, instead of being cosine for the dot product, is which one?
Sine.
Right, good, the sine. There you go, so the magnitude is that measure of orthogonality, so how orthogonal are your vectors? If they're really orthogonal, you're gonna have a bigger cross product. If they're more parallel, smaller cross product for magnitude, and then that's gonna point governed by that way the right hand rule works. So you're going to point with your pointer finger in the direction of the first vector. Then the second vector V is actually your middle finger. So what you'll do is whatever scenario you have, so say if I had something like this. So if this is U and if this is V, and you're looking at this on your page, you're like, okay, so I'm pointing U with my pointing finger, and then it doesn't need to be perfect, but basically is the V going above U or is it going below U? It's going above. So I'm going to orient my wrist like this, which means my thumb is pointing this way out of the page. So if it's coming toward me out of the page, that's positive in that third dimension. Now, if my wrist had been oriented down, say I do a different vector down here, and so I'll call this A. So if I was doing U cross A now, I'm having U, but then now I'm crossing down. So now I orient my wrist down. Where's my thumb pointed? Into. So that third dimension is going to be the negative component. So that's how you use right hand rule. I know you have to use that for physics already, but it's a good refresher.
So, question, the U should always be aligned with the x-axis. Is that the only time we can use that? It's the pointers with the x-axis.
Very good question. Not always. So I could put the U going up, and then maybe actually have, let's see, I'll do an example like this. So, and then we can have V going this way. So now U is not necessarily along the x-axis, but I can still start with my pointer finger going up. And then which way am I going to be tilting my middle finger to get this V? Am I going this way or this way?
This one.
Right, so when I start here, instead of angling my wrist that way to go that way, I'm gonna angle my wrist this way so that I can bring it down. Now, which way is my thumb pointed? So that's always going to give you that direction.
Will be specified, it'll be specified which one's the first one.
Yes, and that order is going to come from that information right there. So you bring up an excellent point, is that U cross V is not equal to V cross U. Suddenly, this order actually matters. If you change that order, you're changing the orientation of your wrist, right? Because that's changing. Oops, I almost forgot a vector arrow. That's bad. Okay. We almost forgot. That's the. So if I do U first, but if I did V first, now I'm starting with my hand like this. So V is I'm pointing at V, and now U is going this way. It's going to be above where V is. And so now my thumb is going in the opposite direction into the whiteboard or into your paper. And so they're negatives of each other. So this and this can be found that they're like the negative versions of each other in the vector. So
the next finger is the X, thumb is Y.
rather than necessarily thinking about it that way, try to think of your pointer finger as whatever vector comes first in a product. And then whatever vector comes second in the product will be the middle finger. What this equals, the direction of whatever happens is then the thumb. Is that clear? Which people are which? Okay, cool. So that's a little bit of a review. And also on the order of review, there is a way you can actually just directly compute. So instead of piecing together and Frankensteining your direction and your magnitude separately, you actually can just go directly with the formula. Oh. How many of you know what a determinant is? Maybe you don't know what a determinant is, but you know how to compute and handle computations with one. So let me write down the two that you're going to need to know. And the reason why I'm starting with this is because basically all the stuff in the application relies on your ability to compute these practically. So I want to make sure you have the comfortable language to express these ideas instead of just being lost the entire time. That's typically not fun. So computational form. I'm going to write that word probably 400 times on this whiteboard. It's a good word. U and V are vectors in R3. So that tells us how many components. I'm going to show you two different ways to denote this. We can say U, so before, in the first lectures, we've just simply said, okay, well, if I have three components, I'll just list three components in my little vector notation and leave it at that. I am going to show you another notation that's probably actually more in the realm of what you're familiar with in physics and engineering, is they'll use the components vector, so U1 times I hat plus U2 times J hat and U3 K hat. Where that's now really explicitly saying, I want that on the x-axis, I want that on the y-axis, I want that on the z-axis. And so then you could also say that V is V1, V2, V3. That's what we have been doing, which is perfectly fine because this is honestly a better notation than this disgusting horrible. And then V1I, V2J, V3K. Is that clear? Right? A little bit of a review. Now, the reason we need to explain what those components, the reason we need these components is so that we can express our formula in a practical computational way. This is what? Is this a scalar or vector? Okay, so we should anticipate having some sort of vector result, right? It's a 3x3 determinant. So the very top row is always, by definition, well, not by definition, in this case, it's a theorem because someone had to prove this, but I, J, and K goes on the top. So there's those coordinate unit vectors. And then we're going to put the components of the first vector next. So the order matters here. U comes first. So I'm going to put the U1, U2, and U3 first. And then V1, V2, V3 across the bottom. Now, I'm going to show you how you can construct this formula using a really nice visual trick. Each one of these is going to get a turn to play, I, J, and K. And here's how it's going to work. When it's I's turn, we're going to pretend like the entire row and column for I are covered. And so all that's left is going to be this little 2x2 down here, right? That's going to be what's in this 2x2 determinant. So if I cover the first row and I cover the first, wow, I got it back. Okay, if I cover the first row and cover the first column, what's left? It's this U2, U3, this V2, V3. And so U2, U3, V2, V3, and that goes for I. Do you see how that goes together? The only thing that you have to deliberately memorize is that we alternate sign. So instead of adding the next one, we subtract the next grouping. Now, J's turn. So if we cover this column of J and we cover that row with J in it, we're only going to have these side flanks, right? The U1, V1, and the U3, V3. So we're only going to have that U1, U3, V1, V3. So we're taking out all the U2s and the V2s. All that second row is gone. Second column's gone. Top row is gone. And then this is buddied up with J. Okay, and then we alternate sign again. So instead of being minus, it's going to be what? So yeah, what's going to be in this 2x2 right here?
Yeah, so we're gonna cover up our third column, which is K. So we'll have U1, U2, and then we'll have V1, V2. And it'll be K hat at the end of it.
Everyone see that? People complain that mathematics gets confusing, but it's really just the abstraction of pattern. So once you get into a rhythm of pattern, accept that it's just a pattern and go with it. If you overcomplicate it deliberately, then I'm sorry, that's just your problem. Now, the formula kind of trusts that you know how to handle a 2x2. So this formula is super powerful if you know how to handle a 2x2. So I'll just, some of us don't always remember these little things, so I'll just write it up here. In general, if you have a 2x2 determinant A, B, C, D like this, who remembers just the way you take care of this? Yeah. Now my memory is really bad, so I just remember it as being like with times when you study history class, like after death, before Christ, things like that. Instead, 80 minus BC. I know, but
There's 33
the
years
worse the
history.
memory tactic, the better you'll remember it.
That's-
That's coming from somebody who doesn't remember anything. Okay. So that's where, so in this case, you apply it to being, you would multiply this diagonal, you'd subtract this diagonal, etc. I'm not going to expand the whole thing out. because I trust you can do arithmetic. The only thing that I will say, don't do this all in your head because you change signs here. So what happens is you'll do it all, and not only are you doing a subtraction in here that might involve a negative sign, but then suddenly you got to remember, wait, was that double negative or triple negative from the parentheses? So, or just write out your steps, and then you can see it, and then you won't get lost. Okay, so write out your work when you do these, to avoid making arithmetic mistakes.
Excuse me.
Yes.
So when it comes to the minus and the plus, is it always that order, or can there be something in the 3x3 matrix to affect the sign?
Oh, very good question. This general pattern is always going to be the same. So regardless of what these numbers actually are, so long as these components are just real numbers, regardless of what they are, this overall structure is the same.
So there'll always be a minus and that'll always be a plus.
This will always be minus, that will always be plus.
Awesome.
Now, I can't guarantee that this actual determinant will always guarantee,
Oh, okay,
positive.
so once you get a number for that, then you'll put it in parentheses.
Yes, yeah.
Oh.
So this is what I graded the labs for this class last year. Of the 27 students, 26 messed this up. So let's get this right, okay?
Yes.
Okay, so the way I'm going to show you lines and planes is I'm gonna invoke an extension of concept because I can. And also because it'll prove to you that you actually already know most of this stuff, you just don't realize it. The hardest part is going to be the creative side, where you're going to have to understand that to get to a concept, you sometimes have to perform little side quests to get to the pieces in formula or the overall general form. But at the bottom of the barrel is really just one concept. And every single thing in lines and planes and 3D and parametric forms comes down to only knowing 2 components at a time. So that's pretty easy so far, right? From high school, what is the equation of a line in a plane?
Y equals mx plus b.
Right, y equals mx plus b, and we have a name for this. This is a very special form because this is our slope and our intercept. So basically, in a math problem, if you're said, here's a slope, here's an intercept, give me the equation of the line, you think to yourself, easy. Miss Johnson in the 4th grade taught me that y equals mx plus b, so you just throw it together. Okay, there is another form. It's the y minus y naught is the n times x minus x naught. And so, but again, it's only 2 things going on here. We have a slope. Well, they put point first. So we have a point with coordinate x naught, y naught. There's a point and slope. The idea is as long as you have those 2 pieces of information, there's a form and you simply put it in the form, right? Nothing about this changes in Calc 3. We will extend the idea, but nothing about this changes. So now in Calc 3, or instead of doing baby math, we're doing prepubescent math. We're going to have the equation R of vector is equal to the vector initial vector naught plus t the variable times a direction vector. So in the same way, I want your brains to do this abstractly. In the same way that we have just y equals mx plus b. R is just your initial plus tb, r naught plus tb. So this is going to be point direction. Ooh. So instead of point slope, it's point direction because now we're in 3 dimensions. So slope is no longer fixed on that xy plane. We can technically go in whatever direction we want in 3 dimensions. Make sense?
So
Yes,
this could be a unit vector and t is the magnitude for it.
Good question. V doesn't need to be a unit vector. V is going to be simply guiding the direction. It will indicate which direction we want the line to go. So in 3-dimensional space, the way that point direction works is we can anchor down a point, and then I can anchor down a direction, regardless of how long that direction is. So here's my direction. And so now what's going to happen is if we parameterize over all values of t, we're scaling this t, and what's happening is we're sweeping out a whole line in 3 dimensions. So as t, that was the worst line I think I've ever drawn in my life. But as you see how if t is going to vary as a scalar, we're going to grow it infinitely large, we can make it negative and shrink it the other direction. And so we're sweeping out a line with only 2 pieces of information, a point and a direction. every single problem involving lines in this class, they might not give you point and direction up front. They might give you instead 2 points. Is that really a problem? Well, not really. Because if instead of giving you the direction vector, if they just gave you, like, say, these 2 points, who's to say you can't use a little bit of critical thinking to get your direction vector from those 2 points, right? Well, now suddenly you have your direction, and then you have a point to choose from. So there are multiple ways to express these lines because it's parameterized. Does that make sense? So memorize this. There are very few things I will actually ask you to just straight up memorize to be able to say, this is one of those. Are there any questions about the definition or what these 2 things are representing?
If you're given 2 points, does it matter which point you pick to use point direction? Because wouldn't they be opposite directions depending on the point you choose?
I'll answer your question with a question. As we range over all values of real numbers t, scaling it, does it matter?
No.
We sweep out the same exact thing. So there are there's going to be many correct ways to represent these. Yes, Axel.
So what does T represent?
T is representing your parameterized variable. So this is the thing that can change. So notice T is a scalar compared to V, the vector. So if T is really small, then that vector scaled is going to be like smaller. But then as T grows, that gets longer and longer. And if I make T negative, now I'm going in the opposite direction, right? So we're sweeping out all of the different,
And so then R, is that an O, like R naughts?
Yeah, like R naught, like R sub 0.
Okay, and
So
so.
that's a point.
Oh, okay. I'll
That'd
address.
be like the base vector.
Yeah, pretty much. So if we have if you're given a initial point, X naught, Y naught, Z naught. The reason why we have to do it this way is because points are technically not the same thing as vectors. So we differentiate from a point. Then we say that R naught is the vector now, where it just adopts those same exact coordinates. So if you were given the point 1, 2, 3, and then you're doing a line from that, this would just be the vector 1, 2, 3, because that's all you're doing. You're taking the point, you're copying its coordinates and pasting it into a vector.
Wait, so, but it acts, so it's a vector, but only has 1 point. Is that what you're saying?
Right, so this point right here, this would act like your T naught, where it's X naught, Y naught, Z naught.
And that's a point.
So the point is just the point.
Right, starting point of the vector.
Yeah, whereas the vector is actually,
Oh, okay.
So, yeah.
So it's from 0 to all
Right.
these coordinates. Okay, I see.
and then you scale the direction from there. Okay. Are there any questions about what any of these objects represent? Because if you know what all 3 of those symbols mean, you've got lines down.
No, I confirm that, that's a parametric equation.
Yes. So I'll show you the parametric form, just so that you have it for convenience. If this is your point, this is your initial vector, and if we're going to say that V is, we'll just call it ABC to differentiate so it's not confusing. So if ABC is the direction, whenever you hear direction, think slope. Basically, it's telling you which direction we're going to go. Then the line R is going to be the initial plus TV. If we substitute everything in, we're going to have just that initial point, coordinates here. And then we're adding the scalar multiple t, which is then the variable, the parameterized variable, times our direction vector ABC. And because you can add components together, this is the same thing as having X naught plus AT, Y naught plus BT, Z naught plus CT. Tell me, is this component a linear equation? If t is the variable and x naught and a are constants, that looks a lot like mx plus b, just but relabeled. So x is now relabeled to t, a is relabeled to n, and the x naught is basically just whatever this is, right? So at the end of the day, no, this isn't new. A line in 3 dimensions is simply a vector where every single component is a line. That makes enough sense, because then the behavior in all 3 dimensions will be linear. So that's pretty cool. So yes, Pearson might say, oh, I want the parametric equations. So then they're just asking you for your components, right? The x naught plus at, the y naught plus bt, the z naught plus ct. But if they want the vector form, they're more interested in this, right? So be able to go between both of those. The parameterized stuff is the components, whereas the actual line is this vector form.
So we can pick any point for the point direction.
So this works for any point in any direction. Yep. You will get plenty of practice with that in the Pearson. So I won't waste your time with crunching 1 + 3 × 4, because if you understand how a line works here, you'll be totally fine.
Is t always given to us?
Okay, so t is, think of t like x in this up here. So it's a variable. It's acting, so r and t are acting like the y and the x. So that's going to be, those are always going to be a part of your equation. The things that will be numbers are like here, you would actually put a slope in there, you'd actually put an intercept in there. So this right here would actually be numbers, and these ABC would actually be numbers. But the t, think of it like a variable, just as it's like a variable x. Cool.
Can I make a comment?
Yeah.
Let's say you don't want the whole line, you just want a line segment. So then you can restrict your t between if you get t by time, time at 0, time at 5, and then you can see how far the particle travels in 5 seconds.
There are 3 examples of skills that you're going to want to be able to do with this. You're going to want to be able to get the equation of a line from a point and a direction. So that's like the most bare bones basic thing. If you're given a point and a direction, can you simply recognize that you just copy and paste it? Okay, so that's step 1. The second step is to be able to then say, okay, I'm comfortable with that. Now, do I understand the concept well enough to get 2 points and take those 2 points and still find my way back to the point and direction? So always go back to point and direction. With 2 points, you can do a little bit of arithmetic to get what this direction is. And then if you have free will, you can choose what points you want to use in that equation. Sometimes you might have, like you said, line segments. So in this case, if you don't specify anything, so like here, if you don't specify any constraint on t, the implication is going to be that t is ranging over all the reals. So t is going from -infinity to infinity. That is the base assumption. So if you just write the equation of a line without specifying anything, you are saying, I want this to be true for every single real value t. If you don't want the entire line, like Dr. Harder said, you can just take a little bit, you can actually specify a specific interval. So if you wanted to maybe go, and you're doing a science experiment, you're curious to see how this, balloon rocket ship that you made with duct tape is going to work. So you start at a time of 0, and you're interested to see how it's going to move just for the first 2 seconds of flight, right? So then, now you're looking at a line that's going to start, and then as soon as you get to t = 2, it's going to stop. So that's how you can generate a segment in space. It's not going to go all the way to infinity. Does that make sense? Okay. Here's the answer to, how am I supposed to know? Well, play with it. That's kind of how that works. Get used to the behavior of how these things operate, and then solve problems, and that should get you in good shape. So let's transition now to planes. We actually kind of, in some way, somebody alluded to the planes on Wednesday's lecture, with the idea of there being a normal vector and then a whole bunch of different vectors that could be orthogonal to it. But before we go into this, I want to clarify a few words. So math words are important. If I say normal, then that means something that is orthogonal to something, right? Normal and orthogonal are going to be kind of synonymous math words that we use. So if I use orthogonal in one case of a definition, then I suddenly start saying normal, have I changed definition? No. Okay. So that's another thing that can be slightly more nuanced in higher math, is we come up with more pretentious words to say the same exact thing over and over again. I think I have, over the course of doing pure math, I have had to relearn the definition of a function 6 times. Wow. Because it just keeps getting crazier and crazier as you go forward.
What does
So-
it entail?
Well, come to topology seminar on Tuesday. They know about that. At any rate, you'll continue to rename things that looked familiar before because what you're really seeing was just a shadow of the actual fuller abstraction. And now you're kind of gaining access mentally to higher levels of mathematical maturity. So with a plane, we're gonna have I don't want to know this. Okay. We're gonna anchor our plane somewhere. So I'm gonna tell you that P naught, X naught, Y naught, Z naught. This point is going to be on the plane. So we're told, here's one of the points. We want this to be on the plane. I'd like to consider this the anchor. Right? This anchors us on our plane. We also need a normal vector. And so conventionally, we call this ABC. This is our normal. Now you might be wondering, normal to what? Well, we're talking about a plane, so might it be too much to ask that we're implying that this is normal to the entire plane. So every single vector contained on the plane will be normal to this very specifically defined vector. And then we have another point, just X, Y, Z. Notice that I'm not subscripting this, which means that this indicates this is variable. So more generally speaking, so this is just now point on the plane generally. We'll be interested. This will kind of, anything that's true about this will be true generally. So we don't lose some level of abstraction. This is going to work for a formula. So what that means is that our formula is going to involve the X, Y, and Z as variables. Whereas the ABC and the X naught, Y naught, Z naught, these are going to end up being just numbers that we plug in, but these are not going to be numbers that you plug in. Variables, constants. Make sense? Okay. Now, how do you guys remember from dot products? There's a very special kind of dot product result that tells us we're orthogonal. Remember what that is?
Zero.
Right. So if I want this relationship to be true always, here's my normal vector. So when I take the dot product between, and then here's my anchor point, and then just a general point on the plane, that's going to form a vector. Let me draw a quick picture because I just remembered you guys are visual learners. Here's 3D dimension space, right? So if here's my anchor P naught, and then now, generally speaking, we have some other. So first, here's our normal vector, normal, and now we're interested in all the vectors that are normal to this. And so all of the points that are on this plane. So here would be all the stuff that's normal. All right. So this, what this is representing right here is any point that exists on this cone. So it could be like right here. So to form a vector, we're going from here to there. This is P. So the vector is formed by starting at P naught as the anchor, and that's anchoring out to all of the P. So this could be a P over here as well. So then you have a vector like that. So that's why we're saying P naught's the base of this vector, and then the head is P. Like you said, what does this have to be?
0.
0. Okay, so now let's plug in what our numbers would be. We have A, B, C, dot. Now to find this, well, we just subtract the coordinates from each other. So we have X minus X naught, Y minus Y naught, Z minus Z naught. That's coming from the fact that since this is the head, it's the tail, this minus this, this minus this, this minus this. Visually, this coordinate minus the X coordinate for there, Y coordinate minus that Y coordinate, Z coordinate minus that Z coordinate. So that's always going to be true for all the X, Y, and Z on the plane.
So the plane is defined by P and PO.
Well, it's actually being defined by the normal vector's relationship to this vector.
Okay, so there's a line made by P and PO, correct?
Mhm.
And N is perpendicular to that line and to that plane.
Yes, it's perpendicular here. Now notice that this, I can't draw like out of the whiteboard, but if I could draw out of the whiteboard, this would be extending out like
I see.
this. Yeah.
What if the line was a curve, like a sine curve?
Ah, very good question. We're gonna get into that when we do vector value functions in the next chapter. So yeah, there's a lot of the similar material that's going to overlap conceptually. So you'll see it all a bunch of times. This dot product is still 0. So then, does the definition of dot product suddenly change if we express a component with two symbols?
No.
No. this is just a number. So we're gonna have A times x minus x naught, right? Because this component times the x component. So it's gonna be, what's next?
B times Y.
Okay, Beverly, what's the third component gonna be?
It's gonna be B times, Z times minus the
Equals what?
0.
0. There you go, that's the formula. So that is quite literally how we define planes in three-dimensional space. So what were the two things we really needed? Well, we needed a normal vector and we needed, there's different ways. This is where, let me put it like this. Suddenly there becomes a lot of different ways you can juggle given information to accomplish the same exact task. So for example, you could do it simply. You could just be given a point and a normal. That's about as straightforward as it's gonna get, right? Because here's the normal, you take the components of the normal, that's your A, that's your B, that's your C. You could take then the actual point, x naught, y naught, z naught, and plug in those numbers, constants, and then you generate a formula. So for example, if I had a point 1, 0, 4, and a normal vector 2, 2, 4, then all I'm doing is plugging in. What's A?
1, 2.
Yeah, because A is coming from the normal vector. So the A, B, and C, those are the components of the normal vector. So that would be 2 in this case. So then it's x minus what?
1,
Good. And then it's going to be what's B?
2.
What's going to be here?
1 minus
0.
Y minus 0. And then what's C?
4.
And then what goes in there?
Z minus 4.
Excellent. Equals?
0.
A lot of people forget this part. And I think that's funny. Because when you say equation of a plane, then you write something that's not an equation. You just miss the equation part of equation of a plane. So yeah, don't forget the equals 0. That happens, unfortunately. You would simplify this to just be 2y. But the idea is that's not too bad. That's called plug and chug. And they've taught crows how to do that. So birds can do it, you can do it. Yes, they actually have. Now, you might not be given the point in the normal. That's okay, because this is what we have on the crows. They can't do this. They can't find a plane from 3 points. Because now this requires some level of human ingenuity. You can't just algorithmically plug and chug, but there is an algorithm for this. If you have 3 points on a plane, you can find 2 vectors and get a normal vector from those 2 vectors. So, here's something that might be important to specify or reiterate, because I know you've heard it at least once. The direction of a cross product is always orthogonal to both of those 2 vectors involved, right? So whenever you did your right-hand rule, you can't like break your thumb off to suddenly not be orthogonal to your opponent, right? So the cross product between any 2 vectors, u cross v, is always going to be the resulting vector, whatever that is, will be orthogonal to both u and v. It's orthogonal to both of them. So we're going to take advantage of that information, because what's going to happen for if you have 3 points, so imagine you got 3 points, just arbitrarily choose one of them to be your anchor, and then figure out through a computation what that vector is, figure out through a computation what that vector is. Now you've gone from 3 points to having 2 vectors in the plane. And from 2 vectors in the plane, oh gee, what's a convenient operation that we have for vectors that gives us an orthogonal vector? So and then take the cross product. So if this would be like u, this would be the cross product is going to give you your n, right? It's going to give you your normal vector. And just approximately 27 minutes ago, you received a formula to explicitly compute from the components of u and v what that cross product is as a vector. So that's why we talked about those determinants. Not because it's cool, but because you're actually going to have to do that probably a few times by the end of the week, okay? So you're going to be taking your 3 points. So the root is 3 points to 2 vectors to 1 cross product, which gives you the normal. And then you have 3 choices. Which point do you use? I don't care, so long as you plug it in correctly. Make sense? So the hardest part is always going to be finding what that normal vector is.
But you said, before that, the cross product between U and V and V and U is not equal, so doesn't that mean we can have a different final result?
Good question. So U cross V is not the same as V cross U, so that might cause concerns like, wait a second, what if I don't set this up right? That's a very valid question. What happens is that when you're talking about the plane is going to still be normal regardless. So the idea is, although U cross V is different than V cross U, they are still both going to produce a vector that's orthogonal to the both of them. So the most important part here is no longer that direction, but rather the resulting vector is orthogonal to both of the vectors. So this whole strategy resides on the fact that we're trying to get that piece of information. The point it's not really the difficulty. We're trying to find the vector that's normal too. So if you did say you did like the V cross U, say you did it that direction, that's okay. Your normal will be different. It'll be pointing in the other direction, but will it still be normal? So you can still use it. So if you thought the line had a bunch of different ways you could correctly answer the question, now there's like a lot of ways you can correctly answer a plane's question. So long as you are showing that the numbers you're plugging in are coming from, yes, I know that this vector is normal to the rest of the plane, and that the point I'm using is actually on the plane. Rebecca.
What final form do you want the equation in? Because like it could multiply out and make it 2x minus 2 and then add together all of the numbers and then it would turn into something that is not nearly as convenient to look at.
Yes. For the sake of, if you have OCD like I do, I always personally kind of simplified everything out. However, I'll save you the time. This is actually infinitely easier to grade, and it is infinitely, it shows that you understand the concept far better than the other form, in my opinion. Because the only way you can really make it look like this is if you understood this. So that's my expectation for you. Do not waste your time crunching arithmetic, because that's not what calculus is about, okay? Learn this form, and the reason why you know this form is because you're going to remember this as a dot product. That's the most important part. The entire equation of a plane is just the expanded version of a dot product because it equals 0. So you have components being added together in this linear combination to give you a 0. Yes.
So you've done the determinant for those two vectors. How do you then plug that into that equation to get the normal vector?
Very good question. Once you take the cross product, regardless of you do it V cross U or U cross V, at any rate, you take A cross product, it's going to give you a normal vector. So what's going to be spit out is your A, B, C.
Oh,
that's what you're going to then take over here.
And but you would also need with the point where the two vectors intersect, would that be the key O point they use in for your x minus x0? Okay. Fine.
Sometimes, and because I am really good at doing lazy math, if this number here happens to be really convenient and easy, like if it's 110 and this is like 749, am I really going to put 749 in when I can just do 110? Probably not. So that's where convenience can kind of come in. You can be creative with that, so long as you are following this form. So long as it follows this form, you're kind of good to go with whatever's on that plane. So another thing that you could do is, so that's with 3 points. Sometimes what happens is you'll be given a line. So you'll be told you have a plane, you want to be able to find a plane from a line that's contained in the plane and an additional point. And you might be wondering, why on earth would we have something like that? Well, sometimes we know that a plane is contained inside of, a line is contained inside of a plane. And what you're going to do is, if you remember, which is okay if you don't, because we just talked about it, that it's R0 plus TV, I'm going to save you some time. If you're ever given a line and they tell you that that line is actually contained in the plane, you have a vector in the plane for free. The very direction of that line has to be contained inside of your plane by definition. So just copy and paste that. Now you have one of your vectors. Why might we need this additional point? Well, one vector isn't good enough for a cross product. We need a second vector for a cross product. So then you can use this point, take its difference with here. Now you've got your two vectors. Why do we need two vectors? Well, to get a cross product, but why do we need a cross product? Because we need a normal. And why do we need the normal? Because that's the definition. Make sense? So it's a matter of how many dominoes fall instead of whether the dominoes fall. Okay, you will always be given a certain combination of dominoes. Maybe you have 5 dominoes to knock over, but they're all going to go down to the same chain of events to get you to this form. So you're never going to be given something ambiguous. If I just gave you 2 points, that's completely insufficient to find the plane. Because those 2 points are only good enough for a line. Those 2 points will only give you one vector. Where are you going to get your cross product from? Then you'd have to make an assumption. So I'm never going to put you in a situation like that. You never have to solve a problem where you have to actually guess. There will always be a path. There will always be, the clues will all be there so that you can get to your point and your normal. So as a matter of review, for the equation of a line, what are the 2 pieces of information you're going to need?
A point and a direction.
Good. So instead of point slope, now it's point direction. Our lines grew up a little bit. Okay, now with planes, what are the 2 pieces of information you're seeking? Good. Will you always be given a point and a normal up front?
No.
No. Do you understand how to use the cross product as a motivating factor to get a missing normal vector?
I think so.
And in the event that the problem's mean enough to not even give you the vectors for the cross product, do you understand how to take points to get those vectors? Okay, so do you see how it just steps back one at a time? So it's not really different problems, it's just one more inconvenience before doing it. Cool. Okay, are there any questions about this on the board right now?
So what is the name of that final equation that we have, a times x minus x naught of b? What is that? What is the term used for that?
This is the equation of a plane in R3.
So, null vector times b naught, b, that's normal. Point normal.
Are you talking about this one right here?
Yes.
So yes, the normal vector, this P naught P is describing the situation where you have some anchor point. Like this would be the anchor point in this scenario, that would be the anchor point in this scenario. It's just simply describing, this is a vector that is on the plane where it's going to give you. And the reason it's 0 is because they have to be orthogonal. So it couldn't be anything else. That's the only reason we can actually use this equation, is because we know 100% sure that if we're going to have this normal vector to an entire plane, that's the thing. So everyone take your notebook, take your pen or pencil or whatever, and stick it up like this. If you were to draw 2-dimensional vectors like that are restricted to the plane of your paper, no matter how you draw that, it's always going to be at 90 degrees if you hold your pen correctly, right? So that's why all it takes in 3-dimensional space is one vector. And if I tell you everything is normal to it, it's going to generate that plane. So if you ever need to remind yourself why on earth it's only one piece of information, because that doesn't seem like a lot of information, just drop your pen on your page and then pretend like you're blind and looking at your handwriting or something. And then you'll be able to see that. I don't have a very big budget. Otherwise I would have built a little contraption or something, you know. Let's see, I gotta get a tub of Connects, some Legos, some things. I left my bowling balls at home just so I don't get kicked out of the school for dropping more bowling balls on the ground here. I did that last year, that was pretty fun. Okay, I'll show you one more thing that's gonna be important from the textbook before I let you guys go. And just so that I'm aware of what's going on, has Pearson Homework been cooperating with everybody so far?
Yeah.
Okay.
That's the sequences and theories on 13.1.
Yeah.
I wish I would.
Wait, actually?
I wish I would have that up.
Review problem.
Oh, the review problem, okay.
Why is this issue?
For a second, I thought you were joking, and then I realized you were
I
talking
wish I
about
was.
that. Yeah.
I wish I was.
There was one where it was like, hey, can you solve this equation? And then it was just algebra. You believe it or true. Which is funny.
How often do those questions show up?
I think there's
Two,
two.
three times.
First 26.
Like, it's almost 3 times which is like what?
Like 20 to 25, but then it's dead. Like, wow.
Okay.
Proportionally very small.
Okay, that's what I was concerned about.
Like 10-15% max.
If it's not many questions, I'm not too worried about it because frankly, that's a good litmus test for whether you should even be in this class. So, okay, so there's an issue of being parallel and orthogonal. I know you've already seen these two words about 400 times since the start of class, but when we talk about parallel lines in the plane, so just think back to high school algebra, what did that really mean for two lines to be parallel in the plane?
They never intersect.
Yeah, they never intersect, but what's the analytical reason for why they never intersect? They're growing or decreasing at the same rate, their slope is the same. In one sense, they're moving in the same what? Direction. Ooh, so then in the plane, if we have in the three-dimensional case, being parallel isn't going to be about slope anymore, because slope is, it assumes you're only in two dimensions here, until we get to partial derivatives. And then for now, with 3 dimensions, if I now have a line kind of going, you know, in 3 dimensions here, and then I want to have another line that's parallel to it. Well, I can't say that their slope is the same per se, but they're moving in the same what? Direction. So when you look at the form, R is equal to R0 plus T direction vector. If the direction vectors are the same, or at least they're pointing in the same direction, you got parallel lines. Here's why I bring this up as a separate thing. A direction vector doesn't need to always look the same. So if I had V, and then I have now this line, R0 plus T times minus B over B. Are these lines parallel?
Yes.
Yeah.
How do you know that?
That's the unit direction, unit vector in the direction.
But this is just the unit vector. We just changed the size. Did we change the direction? No. So the thing that's important to being parallel has been unaffected. They're going in the same direction, but there's a minus sign. Oh no, right? But are we sweeping out the same thing over infinity to minus infinity? Yes. Okay. And then for orthogonal, you can imagine, okay, well, if I have two different direction vectors, maybe R0, whoa, R is R0 plus TA and R is equal to R0 plus TB. If you can show that A dot D is equal to what? 0, then these lines, instead of being parallel, are going to be what?
Orthogonal.
Right. For the reason that they are going to be existing at 90-degree angles to each other. Okay, and then planes are going to be very, very similar, except for here's the thing. A lot of people will look at the line and they'll kind of associate that with everything, make it assimilate the same concept. Just be a little careful about that with the plane, because technically we're defining a plane with that normal vector. So we associate, this is going to sound weird, but the direction of a 3-dimensional plane is actually the direction of that normal vector now. So to have parallel planes, that's not going to come from somehow finding a way to describe how a sheet, it has a direction. That direction is going to be given by the normal. So parallel normal vectors is going to be what we mean for parallel planes, and orthogonal normal vectors. So that's where if you have like, here's the normal vector for plane 1, and here's the normal vector for plane 2. What do we want this to be if they're orthogonal planes?
0.
Yeah, same idea. So do you see how we're not really talking about anything new? We've recycled the same like 16 definitions about 4,000 times. It's like going to Moe's. You know, you think you're getting new food when you get the bowl versus the burrito, but they're lying to you. They're just putting the burrito in the bowl without the tortilla. So that's kind of how we do all of this parallel orthogonal and everything. If there's no questions, you guys are dismissed. Do the readings. I'll see you lab Friday.
Reading score 30.5.